this is my operator V, which is written as Vx. Vx is a real function like Coulomb gas, okay, a Coulomb interaction 1 by R. Now I have destruction operator at x and creation operator at x, okay. So this is an operator, no, Vx is a function, but I have to integrate over full space, okay. So how do I compute this, or how do I act, this will act on some state, and how does it work, okay. So let us rewrite this in Fourier momentum Fourier space. So yeah, you have to just see this this line, it just looks complicated, but it is not. So psi dagger x, I am just writing this part as this in Fourier space, okay. So what is psi dagger, which is in Fourier space, it a dagger p exponential minus I p dot x and integrate. So this is p2, okay, I made a mistake, this p2, right. So this is the definition. So this creation operator in real space is written in Fourier space, and as I said, lot of calculations are done in Fourier space, okay. It simplifies, and in fact all the Feynman diagrams you might see 2 photons coming, the going out, these are basically the wave numbers, photons with wave numbers k1 k2 coming, scattering, okay. So that is what we are doing it here. This particle we are just going to specify this psi dagger as in terms of various wave numbers. Now this part psi x I am going to write as here, okay. So this is psi x, Vx is a function, a real function, is not an operator, so it can be shifted around, okay. But I cannot change this, this cannot go to the right, psi dagger is to the left, okay, psi dagger cannot go to the right. So this is psi x, which is coming with a plus sign I p1 dot x, okay, this we defined it, okay. So this Fourier stuff, please remember the definition, I am doing it in 3D. So divide by 2 pi cube is there. Now Vx I am going to again Fourier transform it, but this is just simple function. So this Vp is a real well complex number, and is just that. So now this so there is a dx part, right, there is a dx d cube x is there. So what will I do with d cube x? So let us do it here, d cube x. So d cube x will act only in the functions, because a p, a dagger p, they are all momentum space operators. They, d cube x cannot do anything on these Vp, a dagger and so on. So it is going to act on exponential I minus p2 dot x. So x we remove it outside, let's put plus p1 minus p2 plus p dot x, okay. What is this object? These are vectors, huh? Is a delta function, no. So 2 pi cube delta function, okay. So great, so we got, now I can compute this. So well, I can't compute this by, I am rewriting it. So this is p1 and p2, you have a dagger p2, a p1, they are just coming from here, and so this Vp, right. So this is a delta function, so I can write p as p2 minus p1, no, from here. So minus p2 plus p1 plus p is 0. So that means p equal to p2 minus p1. These are vectors, of course. So this is what I have written it here. So I need to integrate this. So this is my operator written in Fourier space, okay. Of course this will act on, so imagine that I act V on number operator on state psi. So psi will have some number operators, like there will be 3 particles, if it is boson 2 particles. So it will just see whether well, it will look for wave number p2 and it will increase by 1, this one, and look for wave number p1 and decrease by 1, okay, and Vp is a function. So we compute in that way. So basically these are going to act on the state which is just stated, well, given in terms of number of particles in various wave numbers. Okay, so this is how we write, and in fact we can write a Feynman diagram for this. So how is Feynman diagram written for this? So we write V as a some kind of blob. You can think of this as a Coulomb scattering. Okay, so this V is a Coulomb scattering. Now this A is a particle coming. Okay, the P1 is a particle coming. P1 is a particle coming, and is getting destroyed. This is getting destroyed, and what comes out of this thing is particle P2 comes out of this. Right, this is the creation operator. So this part is written in like that. Okay, so coming in is P1, P1 is so you just imagine that shoot a particle P with momentum P1, this guy will destroy it, then V will act on it, this V is acting, well, V is going to be appearing, V will play a role, and then it will eject a particle with momentum P2. So this process has amplitude coming from this potential. Okay, so A dagger and A P1 and A dagger P2 will give this amplitude square root P2 minus P1 square root P1 and that, and multiply by V and just sum over all P1 P2. We will do one concrete example. So I hope this is clear. Any given state we have to just do it for each piece and then just integrate it or sum it up. Okay, and that is how it is done. I mean, this is not big magic, but this is how it is done in field theory. Okay, we'll encounter some of this in future as well. So a density matrix you might have heard of. So the density matrix is defined as this: psi dagger x I x is a one destruction and one creation. So okay, and this is a definition, and we write this operator. So this is operator, no? And well, this V operator is written like that. Okay, and right now I am just giving the definition. I am not really discussing more on this. Okay, now let us do this more complicated example. So Hamiltonian is this looks complicated, no? When this is a creation destruction operator here and this destruction creation operator here, and their amplitude E naught here and this V by 2. But let us imagine that only 3 states are possible. So P is only 3 of them. You can call it K1, K2, K3. Okay, so 3 wave numbers you may call. A 3 wave number. So what is this guy doing? Is a destroying for that wave number and creating. So I write my state as number of particles in P1 state, P2 state and P3 state. So what does this guy do? First operator. First operator, let us look at D dagger P1, D dagger P, dP. I have to sum over all P's. So imagine that I have 1 0 0. So here this is 1 and these 2 are 0. So there is only one particle, but that is in P1. So what will it give you? So this, well, I have to sum into all P's. So this implies D dagger P1, dP1 plus these are operators. This D dagger P2, dP2 plus D dagger P3, dP3 acting on 1 0 0. So what is the this guy do? dP3 0, no, there is 0 particles, so this is 0. Second one 0, third one 1, right, because this is acting on here, is creates is 1. In fact, these are number density. So there 1 particles will give 1. If there was 2, then it will give would have given 2. So this gives you 1. Okay, so we can these are basically, this matrix is going to be, you can make a guess. So these are matrix, matrix is going to be 1 1 1 diagonal. So, that is what it will be, but this is more complicated. So, let us act, so you can act this operator. So, I think I have, okay, yeah. So, let me explain. So, I hope this part is clear. This is diagonal, this guy, it looks diagonal, no number of, so you will get that. Now, here I have to sum over P1 and P2, and this is destroying P2 and creating P1. So, let us imagine I am working on this sum. So, there how many terms are there? There are 9 terms. Okay, there are 9 of these. I had only 3, but there are 9 terms. So, which ones will be non-zero? So, destroying one, this will destroy this one, and create anywhere. It can create one at third. So, is destroying this particle, but it can create here. So, let us write D P1, which is the first, this one, D dagger P3. What will that do? Remove one, so we will remove this and create a third. So, we will create 0 0 1. Okay. The one which is D dagger P1 D P1, which will be this 1 0 0, it destroys and creates, and D dagger P2 D P1 will be 0 1, no, is destroying here and creating at P2, so 0 1 0. So, this is what we got here. Okay. So, there are 9 terms. When it acts on this state, it creates this. Okay. So, I can choose this as my basis vectors. My basis vectors are 1 0 0, 0 1 0, 0 0 1, and I create a matrix as operator, right. That is what you do in quantum mechanics. And your operator is just to see destroy, create, and here I did not have to worry about square root NP plus 1 in NP and that, but you need to worry about that, and that is it. You can construct this operator, and this is what I wrote. This E naught is a prefactor. So, this is a diagonal matrix, and this one will be 1 1 1, all ones, right. 1 0 0 acting on this operator is 3 ones, right, in the first column. Then you act on 0 1 0, I will get the second row, 0 0 1, I will get a third row. So, this is my operator, clear. Okay. Now, what is the eigenvalue of this? You can make a guess, eigenvalue for this, sum of 2 operators. So, what is the eigenvalue of this? 1 1 1, 3 eigenvalues, 1 1 1. What about this? Great, some very good. So, this is, this one, the trace is 3 and determinant is 0. So, and you can see if you have vector 1 1 1, it gives you eigenvalue 3. Okay. So, this one has eigenvalue 3 and the other 2 are 0 and 0. You can just compute them, okay, but it is a good guess, somebody gets it right. So, we have this one is 1 and this 0 0. So, you can just add them together. So, eigenvalue is E naught plus 0, E naught, and this will be E naught minus 3 b by 2. So, these are 3 eigenvalues. In fact, we know the eigenvectors as well. So, this one corresponds to this one, this is eigenvector is that, and 0 0 1 you can easily construct, no. So, we have to just construct for this. Diagonal means any vector will be eigenvector, so that is no worry. So, 1 1 1 1 1 1 x y z is 0. So, this is 0. So, we have x plus y plus z is 0. So, just choose. So, I can choose minus half and 1. Okay. So, and that one more option is minus half, that the 2 independent options minus half, 1 minus half. Okay, just choose 2 of them and you will get 0 0 eigenvectors. So, 3 eigenvalues and so this corresponds to this 1 1 1, this is the eigenvector corresponding to this one. Okay. So, we can write down operators with particle with the field theory. So, it is not very mysterious, I mean just have to work out and remember the rules, and this is taken from that book Quantum Field Theory by Lister and Blundell. Okay. So, this book is top reference in my notes. Okay, the last one, I think I know two more examples. So, tight binding model, you might have heard this, no, tight binding model in condensed matter physics. This is one of the very important models. So, we destroy a particle at site j and create one at I. So, this is hopping. So, this electron is hopping from j to I, is called hopping. Okay. So, how do I write in terms of field theory? Okay, very easy, no. So, you destroy a particle at j and create at I, that is it. So, the Hamiltonian is written as destroy at j and create at I, and this is an amplitude for that. So, once you know the rules and you can easily write and you can understand what they are talking about. Okay. So, the last example, okay, fourth one. Now, this slightly complicated looking operator. Okay. So, we have 2 particles coming in, it interacts with this potential. So, this is like basically the 2 electrons coming, interacting with potential and getting off, and they are getting off here. So, we can, objective is to write this in Fourier space. Okay. So, I will do exactly same algebra what I did in the first slide, or okay. So, let us just do it bit quickly. So, there are 4 operators, okay. V is not an operator, V is a function. So, 4 operators P1, P2, P3, P4, and these are the 4 wave number operators in wave number space. So, these 2 correspond to these and the creation operators correspond to these. Okay. So, P3, P4 are the outgoing momentum and P1, P2 are incoming momentum. Okay. This is exactly like what Feynman language, incoming momentum and outgoing momentum, and we have this exponential coming from this Fourier transform, this one, and this is getting cut Vx minus y. So, this Vx minus y. Okay. So, clear, no? So, and this is integral d cube x here. So, this part is the real space integral. Okay. Now, this is function of P1, P2, P3, P4, this whole object, x will be integrated out. Okay. So, potential will have all the momentums. Okay. So, we write, so this is a bit of manipulation. So, P3, P4 minus P1 is written as Q, well you will see why. Okay. P3 minus P2 is written as minus Q. So, our operator looks better. So, if I write like this, okay, so then you will get x minus y. Okay. So, this is just algebra. Huh? So, this is x and y. So, there 2 of them are with y and 2 of them with x. So, there is a typo here. So, P4 minus, so P4 minus P1, this Q. So, P3 minus P1 is minus Q. So, this is x and this is y. Okay. So, I have to write this is psi y will be, okay. So, let me tell you, P1 is coming with here, P1 is coming with, no sorry, this P1 is coming with x, P1 is okay, depends whose I am using. So, what this is y. So, this P2, P1 is coming with y, P2 is x. So, P2 is x. So, this is P2. I am expanding this as P2 and this expanded is P1. Okay. So, P1 is coming with y, alright, and here also P3, this guy is coming with x P3 and this is coming with P4. Okay. This momentum these are dummy variables P1, P2, P3, P4, but I have to keep this track of x and y. Okay. So, this is my this real space integral. Okay. Now, you see this is the only function of, so I get rid of x minus y, okay. Actually there are two integrals, d cube x, d cube y, there are two integrals here. So, this will be function of what? This whole thing real space integral, only function of q, because x will be integrated out, y will be integrated out, only momentum. So, we write this as v of q is a real, well, it is a complex number, but v is v of q, okay. So, we write this as v of q, okay. So, this is how I compute. Now, given the number of given the state, I just have to destroy two of them and create two of them, okay. So, how do I write this is a Feynman diagram, okay. So, let us bring these particles P1 and P2. So, incoming is P1 and P2, no, P1 and P2, outgoing is P3, P4, okay, and they exchange via this propagator. Well, this v, okay, this is v of q. Now, so this should be straight line, no? They are not bending. There is no. So these are straight lines. These are incident fermions, 2 electrons. So P4 minus P2, P4 minus, no, I made a mistake. This P1, this P1 and this P2. These are labels. I had to respect this. P4 minus P1 is P4 minus P1 will be. So this is, I add P1. So this Q, right? P1, no, Q will be inside. Is it clear to Q1 is, so Q1 is coming in. So look at it here, P1 plus Q equal to P4, right? Can you guys see this? P1 plus Q is 4 P4. So P1 is coming in, Q is also coming in, and that gives you P4. Momentum must be conserved, okay. So P1 is coming, P2 is coming in, okay. So here P3 minus P2 is Q. So you get here. So Q plus P3 is P2, right here. P3 plus Q is P2. So it's true, P2 equal to Q plus P3, okay. So momentum is conserved, momentum must be conserved at this called vortices, okay, and this is a Feynman diagram, okay. So we have two particles coming with wave number P1 and P2, they interact via this VQ and they get out with P3, P4, and now I have to sum out all possible momentums. So imagine that lots of particles are coming in, you have to destroy and create, and you have to just sum them up. This is how you compute this V operator. So actually what will be there, V operator acting on psi, it gives you phi, okay. So V or V operator acting on psi will give you another state phi, okay. So this will be lot of number state with numbers in between. Now this will be another state with numbers in between, and of course there will be some prefactors. The prefactor will be function of Q, or rather V, function of V. So potential will come in here, potential effects will come in here, okay. So this is how we compute, basically this is how you calculate in field theory. You construct operators, you bring in states of, and then you will state will act on the operator and give you a new operator, a new state, sorry, new state. Okay, any questions on this? So these are interactions, huh? So we have free particles and they interact with these potentials. We will have more complex interactions in future, but this is a kind of simple Hamiltonians. Okay. Okay, so Yeah, anyway, so this is well, I rewrote this in terms of we can get rid of one of them. Okay, so if no other question, then I will do the last topic for today and then we will quit. Well, right now think of external. Example 1. Example 2 could be the two particles are coming and there is a some again Coulomb potential, but is or actually you can also think of potential. Well, do not think of Coulomb, in fact you think of Coulomb of these two particles itself. So, repulsion of these two particles. So, 1 divided by mod x1 is y with photons, that was V is photons, you can think of photons propagator. Okay, that is that was what Feynman diagrams are. So, this V is a potential, this is a electromagnetic field. Right now we simplified it, but that is a Coulomb interaction. And the in between example that we had V of d dagger P1, d dagger d P2, that is more like a solid state thing where there are 3 states in atom, and we have photon coming and hopping. So, laser kind of thing, that could be an example.